So last example where we're finding, we're doing a hypothesis test involving means. Okay, so a researcher believes that the average lifespan, so now we know we're talking about averages, okay. So a researcher believes that the average lifespan of large breed dogs is less than 12 years. All right, the researcher finds the following data. Use significance level of 0.05 to test the researcher's claim. All right, so this is much different in that we aren't given a sample mean and sample standard deviation. Does that scare you? No. Why?
We can calculate it.
We can calculate it, right? Okay, so that might be one of the first things that you want to do. All right, and I think that would be a great first step. You're given a sample, you know you're about to do a hypothesis test, you know you're going to need the sample mean and sample standard deviation. So I think that's a great place to start. So how do you find sample mean?
Take the average.
Right? Yeah, add up all the numbers and divide it by the sample size, right? So the sum of all these numbers is 56. What's the sample size?
5.
5. There's 5 numbers there. Equals 11.2. All right, you might be out of practice with finding sample standard deviations, but if you are, now is a good time to get in practice, right? We're about to have our final exam. You know you're going to have a sample standard deviation question in there. You know you're going to see probably a question like this. We're going to have to calculate a sample standard deviation. So pull out your formula sheet and remember how to do this, okay? I'm going to go ahead and tell you what the sample standard deviation is for this problem. I highly recommend that you calculate it yourself. You pull out your notebook and you remember how to do it. You calculate this yourself and see if you get the same number. I got 2.3875. Okay? If you want to go in Blackboard and have a discussion about this and see if you want to talk about how I got this, if you get something different and want to talk about it, go ahead and post it to Blackboard. Love to talk about it there. But this is what you should get. You should all be able to calculate that. Okay? All right. So now let's get into our hypothesis test. Let me write down n equals. N equals what?
5.
5. Okay. So that's all my sample things that are sample parameters, sample statistics. Okay. So step 1, all hypothesis test is to state your null and alternative. Okay. So we know we're testing average. Average what? Average lifespan. So we're testing an average lifespan, so we know we're going to have mu there, right? If we're testing a proportion, we have p. So testing an average lifespan, we have mu. Null always has the equal sign. What do you think it's going to equal?
12.
12, right? Researcher is testing if the average lifespan is less than 12 years, right? So they are testing something, the average being less than 12. And where they got 12 from, who knows? I mean, they could have gone, maybe that is that's what people, obviously that's what people believe. Why else would they test that, right? So people must believe that large breed dogs live 12 years, and this researcher thinks it's less than that, right? Okay, so it equals 12. All right, so what's the alternative? We know we're going to have 12. These numbers should always match.
Not equal
So it's
to?
just the sign. Not equal to?
You said the researcher believes the
Average lifespan.
Oh, is less than 12. So less than 12.
Yeah. No, that's okay. Yeah. So let's highlight that. Is less than 12. So the researcher believes that the average lifespan of large breed dogs is less than 12 years. So we are testing.
It's written very clearly.
It is written very clearly, right? All right. So what size test is this?
It's a left.
It's a left tail test. Remember, there's a right tail, two tail, and left tail. I'm now doing a left tail. So I've done all 3, right? Okay. So step number 2 is to calculate your test statistic. Now, Remember, we go to our formula sheet. We're trying to calculate a test statistic. We go to test statistics, chapter 8. And there's mean, sigma known, mean, sigma unknown. Which one am I going to use?
Unknown.
Why?
Because n is less than 30.
Ah. Okay, n is less than 30. You know what? I am missing something really important right here. Let me add a statement to this. Use significance level 0.05 to test the researcher's claim. Let me add to this. Assume that, let's see, lifespan of large breed dogs is normally distributed. Okay?
That made all the difference.
Maybe not to you, but it did to me. Because without that assumption, you would not be able to move forward with this test. Okay?
Oh,
now, when you have large sample sizes, now you remember in previous section we were talking about the central limit theorem. Okay? And we talked about when you have a large enough sample, and we said 30 was good enough to be large enough, then in order for the sample mean, x bar, to be normally distributed, when n is large, you did not need for the original data to be normally distributed. Okay? But when n is not large, so n is small, then the sample mean will only be normal if the original data is normal. Okay?
Okay.
So lifespan is it's okay. That's not a far out assumption, right? Income is a far out assumption. Income is not normally distributed. It's well known, right? It's skewed. So if you had a small sample size and you were testing the average income, then go get a statistician because you can't solve that using the methods we're talking about. Or get a larger sample size so that you're able to use the method that we talked about earlier. Make sense?
Okay, so the larger the sample size, even if your population mean, let's just say it's income and it's not normally distributed, with a large enough sample size, then the distribution of the sample mean is tends towards normal.
Yes.
Okay, but the smaller it goes, the more obscure the distribution is, so it becomes less normal if that's what the underlying population was.
Yeah.
Okay.
Think about it. If sample size is 1, then your sample mean is just one of your data points, right?
Mm-hmm.
So in the extreme case where your sample is so small, the only way this is going to be normally distributed is if your original data was normally distributed.
Got it.
But when sample size is really large, this will go to a normal distribution. Okay? So that's what the central limit theorem is all about.
Okay.
So we talked about that earlier in the semester. Okay, so, alright, so good. So we need this assumption in order for us to move forward. Alright, because we're going to have, you don't need it when you have large sample size, but you do need it when your n is small. And so n is so small, we're going to be using this t statistic. Okay, it's exactly the same as the z statistic that we did in the previous videos. The only difference, right, and the very important difference, is that instead of having sigma here, we have s. And s is the sample standard deviation. Right? Sample standard deviation. Okay? Alright, so we have everything we need to calculate this. So this is 11.2, right? That's a sample of these numbers, sample average of these numbers. Okay, mu, always assume the null is true. 2.38. Okay, by the way, I rounded this to 4 decimal places, the sample standard deviation. You should also do that because you want to make sure t is accurate up to 2 decimal places at least. So you want to make sure you don't round too much in intermediate steps. Over square root of 5. Okay, if you're plugging into your calculator, make sure you have the numerator and denominator in parentheses. Plug it in, figure out what it is. I got negative 0.75. Okay, that's what I got. Negative 0.75. Step number 3, p-value or critical value. Remember, we've talked about that? Well, turns out when you go to your t-table, by the way, I just said t-table. Why are we going to t-table instead of z-table? What's a t statistic, right? And you'll know it's a t statistic because it says that. It says t on your formula sheet. It says t instead of z there. So you should be going to the t-table. Now, t-table looks a lot different than a z-table. And it operates a lot differently, too. And if you notice up top, it says critical t-values. So, this t-table is just critical values. You cannot use this t-table to find a p-value. Okay? Using technology, aka your computer, right? In my stat lab, I think there's a t calculator of some sort that you can use there, or you can just actually, if you Google t distribution calculator, you can find p-values by just Googling it, right? And the way you would find it is, well, in this case, it's identical to a z table, except you're just using Google instead. Okay, so
So why isn't there a chart?
well, that's a good question. Okay, well, why isn't there a chart, right? There's additional thing here for the t distribution called the degrees of freedom. So let me talk about the critical value. Okay, so first thing you need to know is degrees of freedom, which is n minus 1. It's always going to be your sample size minus 1, which is what in this case?
4.
5 minus 1, which is 4. Okay, so there is one row here that corresponds to degrees of freedom being 4.
What is the degree of freedom?
It basically changes the way the distribution looks. So you know how normal distribution, it looks like this as mean 0, standard deviation 1. That's what the z distribution looks like, right? Well, for t, it looks very similar to a z. If your degrees of freedom is really large, then it looks, say this is what the normal distribution looks like, then it'll look exactly like that.
Mm-hmm.
So let me say degrees of freedom is very large, say infinite. If your degrees of freedom is really small, then it looks more like this. It's got thicker tails. It takes a longer time for it to kind of go out. It's got thicker tails than the normal distribution does. So it's basically an entirely different t distribution. It looks different than the normal distribution because it has thicker tails. And its tail size is dependent on how many degrees of freedom you have. So they're really thick for small degrees of freedom, and then they come to look just like a normal distribution for really large degrees of freedom. Okay? So the distribution, actually, it's different. There's a different distribution for every degrees of freedom, which is why I don't have 100 z tables, which is what it would require, but I have just one row per degrees of freedom. And that's why the table looks different.
So if I Googled a p-value with using a t statistic, it would need to know my degrees of freedom because it would use that specific distribution.
Yes. If you Googled it, it would ask you what the degrees of freedom is. You would need to plug that in, and then it would use like a complicated algorithm, a calculated calculator to basically come up with a more complete table for each of these rows.
But technically, if on a test, we only have 1, 2, 3, 4, 5 data points, you could provide a t-table for degrees of freedom 1, 2, 3, 4. Like you'd have a t-table for
but
df1.
I'm only going to provide you with this table.
Oh.
So I'm only going to ask you to find critical values, which I'm about to talk through how to find that.
Oh.
So you're not going to have to find p-values on a test on an exam. Okay?
Gotcha.
You're not going to have to find p-values on a t-test during an exam that you take in this course. Okay? You're only going to have critical values. On a homework assignment, you might have a p-value, for a t-test, you'll need to use a computer to do that.
Mm-hmm.
Okay?
Tricky.
Alright. Okay. So now we know what degrees of freedom is for. So critical value. So when I draw this, I'm going to draw it, it's going to look like a normal distribution. But remember, this is a T distribution. Okay, with thicker tails. So this is, again, this is the distribution of T, right, instead of Z, assuming HO is true. Okay. T distributions are also centered on 0. So I always have 0 in the middle. So let's just do it with their tails. That makes them different. Alright, so this is so I'm doing critical value. It's a left tail test, right? So that means my critical value is going to be on the left, right? This area here is going to be what?
0.05.
Very good. Right, and this area, this is going to be my rejection region. And this, what is this cutoff? That's basically, that is what the critical value is. I need to figure out what this cutoff is. Sometimes you use TC to note critical value, and I'll use TS for test statistic. Okay. So I go to my table here. Now it says area in one tail, area in two tails. Why do you think it separates it out like that?
So the tails are not symmetric?
Well, so it is symmetric. It's still symmetric distribution, just like a Z table.
Oh.
Because we have two-tailed test.
Yeah, but you can't just times it by 2 like we did in the other one?
Yeah, but the way this table is working, it's not giving us. I mean, area in one tail is 0.005, area in two tails is 0.01. So yeah, you can just go from one to the other by timesing the area in one tail by 2. Yeah.
Okay. So it's
okay. So
unnecessary.
yeah. So, well, I guess. Okay. Anyway, since we're doing a left tail test, which is not two-tailed, we're going to use area in one tail. Make sense?
Mm-hmm.
Okay. So we match it up. So you only need 0.05, right? So it's that one right there. Okay, so 0.05. Now I go down to 4 degrees of freedom. And I get 2.132. Alright, there's something wrong with that. So that is what it says on the table. But there's something wrong with that. Do you know what it is? Here's 0.
It's greater than 1. It's not negative.
It's not negative, right? So I need to be careful. This table will tell me always a positive number. So based off the direction of my test, I need to know is it positive or negative. It's because the left tail test, that's why it's a negative number. Make sense?
Mm-hmm.
Okay. So is my test statistic in the rejection region?
No.
Oh. Right, it's not. This is negative 0.75. It's not beyond negative 2.132, right? It's not over here. Yeah? Alright, so then I'm ready to write my conclusion. Step number 4. So it's not in the rejection region, so we will fail to reject HO at significance level 0.05. And step number 5, so we failed to reject this, so there's not enough evidence for the alternative. So there is not enough evidence to suggest that the average lifespan of large breed dogs is less, right, have it match the alternative, is less than 12 years. Okay?
Mm-hmm.
Make sense? Any questions about that? Okay. So just real quick, I just want to clarify this for a minute. If you were to do a p-value, your degrees of freedom would still be
4.
Yeah. So I'm going to just for a minute, let's just talk about this real fast. So if you were to do a p-value, you would need a computer. So I'm not going to do it right now. Okay, but what would you need to plug into the computer? What would you need to think about? So in the center of E times 0, remember p-value, you always use your test statistic, right? So negative 0.75. You basically would want to know what's this area. So you would go in, so that would be the p-value, right? So you would go online, there would be a calculator that says, well, what's the degrees of freedom? And then you plug it in. Well, what's your test statistic value? What's your test statistic value? And you would plug it in. And then it always would give you the area to the left, just like a table would. So that's the area to the left, so you'd be good. That'd be your p-value. Okay? So go in and Google p-value, or go in and Google t-distribution calculator or something like that, and figure out what the p-value is. It should be some number more than 0.05, because it should match these conclusions. Okay? Alright. Any questions? Alright, thanks.